if we have the observations x sub 1 through x sub n from some random sample drawn from some Bernoulli theta distribution, and we want to find the MLE, the maximum likelihood estimate of that theta, how can we go about that, right? So you might immediately start thinking, okay, what's the PDF of a Bernoulli theta? And it's a bit strange. Usually it's given to you as a discontinuous, right? As a case-by-case PDF. So it'll be, okay, it's theta if xi is 1 and 1 minus theta if xi is 0, right? But you can kind of think about that intuitively like this, right? Where it's theta to the power of xi times 1 minus theta to the power of 1 minus xi. Because if xi is 1, my 1 minus theta goes away, right? So that's where we get our likelihood function here on the left-hand side, this product. So we're just multiplying over all of the xi's, that PDF that I just mentioned, that you should remember is only defined on my xi from 0 or 1, right? So those are my only two possible values of xi. Now, if I take the log of that likelihood function, which is my L of theta, my small l of theta on the right-hand side of this line here, due to the properties of logarithms, we use the natural logarithm in statistics, but it doesn't really matter. We can move out our xi's in front of this each guy because our 1 minus xi and our xi are the exponents, so we just move those out. And then the other thing we can do is everything becomes, a sum. So that's why I remove my product and I turn that into a summation from 1 to n. And that's also why my two lns, I'm just adding them together. Now, our next step, right? Remember, we're dealing with maximums here. So if we want to find the maximum, your first instinct should always be to, take some derivative, some sort of derivative and set that equal to 0. So in this case, we're just going to take the derivative of our log likelihood function, not our likelihood function. And you could do the regular likelihood function, but our log likelihood function, as you see right now, it seems to be a bit easier to take the derivative of that because we're not dealing with any of this product rule stuff. So if I do that right here, you'll notice that I'm just using the properties of logarithms again. These guys really come in handy with maximum likelihood estimates. So I'm moving my xi to the top of a fraction divided by theta minus my 1 minus xi divided by 1 minus theta. And I'm just summing over all my xi's. And then I'm simplifying that fraction. And remember, the key insight here, I should say this quickly, is don't forget to take out your negative, right? The reason I have a negative between my two fractions is because within my ln, I have 1 minus theta. So remember the nature of the chain rule. Review that if you don't see why there's a negative in front of that fraction. So yeah, after we simplify those fractions, we're setting equal to 0 because we want the maximum. And we can kind of ignore the denominator. And then that will apply that theta needs to be our sample mean x bar sub n. And the reason for that, if it's not immediately clear, you should verify this on your own, as in move the negative theta outside of that simplified fraction summation to the other side and solve from there. But pretty quickly, it should fall out. So some people would say, okay, like we're in the money, we're done. And depending on what class you're in, that might be okay. And I'm not saying, they might just say, just assume if you find a maximum, it's a maximum. But if they don't, remember that in statistics, sometimes you want to check it, you just take the double derivative of your log likelihood or your likelihood, and then you check that it's less than 0. For this case, that's sufficient to show that I'm a maximum. So all I'm doing here, right, is I'm doing that again. So I'm taking the second partial derivative with respect to theta of my log likelihood, and again relying on the properties of logarithms and derivatives of fractions. And the big insight in this line is just my little trickery, my little voodoo in the middle here, where all I do is, okay, let's take a step back first, right? In the middle of this guy, what I'm doing is I'm summing from 1 to n, over all my xi's, and x bar, right, is just that sum divided by n. So that's why I can kind of do this little manipulation here on the top of both of my fractions in the middle of this last line here, because n times x bar is going to be that sum. And the reason I can do that for each of them respectively is because you can distribute the summation, right? If you did that before, that would become clearer. So you should check that this works on your own if you don't see immediately why this works. Now, I have this right bar here right after that, because remember that we have to plug in our MLE to check that that MLE is actually the maximum, right? It's not sufficient to just look at this part here and see, okay, is it negative? Over what range is it negative? That's not enough. Plug in your MLE. So in this case, theta is our x bar sub n. And when we plug that in, you notice that on the bottom, we have 1 minus x bar squared, which we can eliminate, our guy on the top. And then we also have x bar, we can eliminate our guy on the top. And this is always negative because, this is always less than 0 because x bar is a proportion, right? So a proportion, by definition, is between 0 and 1. And again, you can verify that this is always negative, graph it if you want, and then we're done. Yeah.